So this chapter is going to be lecture 2, part 2. Sorry, this video is lecture 2, part 2 on chapter 13. And this really talks about what is the rate law. Okay, so that's kind of the goal of this chapter, talking about the rate law. So the rate law is defined as an equation that relates the rate of a reaction to the concentration of reactants and catalysts raised to various powers. Okay, so really the rate law, or this is what I would like to call the generalized rate law, is going to be all of the reactants and the catalysts. That's this stuff here, not the products. Okay, and it's the product, it's the multiplication of all of these concentrations. So rate is equal to K times A to the M, B to the N, and C to the P. Okay, where M, N, and P is experimentally determined and has to do with the rate order, not the rate or the stoichiometric coefficient or the molar coefficient. It has nothing to do with this. So this A and this B has nothing to do with the generalized rate law. Okay. So M, N, and P is the exponent related to the concentration of that species in the rate law. And these orders, M, N, and P, are experimentally determined. Okay. And the book gives you 3 examples. You have C3H6 here. And so it's raised to the first power here. You have NO and H2 is raised to the second power, and here it's an invisible, the first power, okay? And here you've got these 3 reactants, and it's raised to the first power, the 0 power, and the first power accordingly, okay? So to figure out the overall rate order, you just need to add the exponents together. So here is just the rate order is 1 overall, okay? Here, 2 plus 1, overall rate order is 3. Here, 1 plus 0 plus 1, the overall rate order is 2. And with these rate orders in hand, you can actually calculate the unit for K based on the generalized rate law. Okay, so remember that rate is equal to the concentration or the change in concentration over the change in time. That's from video, the lecture 2, part 1 from the last video that we just watched. So rate is equal to the change in the concentration, that's molarity, over the change in time, that's seconds. It is equal to K, and in this case it is first order, so the concentration, the units are molarity, and it's raised to the first power. In this case, the units for molarity is, I'm going to divide it by M, divide by M. Okay, the M cancels out. So really, K on the right side is equal to M over S divided by M. The M cancels out. So really, it is 1 over S. Okay, or we can say S to the minus 1. Okay, so that's what the units for K are. Now, if you have 2 and 1, okay, the overall order is 3. Okay, or we call third order. So again, rate is M over S. And now we have it raised to the second power and raised to the first power. Again, concentration is always expressed in molarity in this chapter. Okay? So really, M over S is equal to K. Now, M squared times M to the 1 is going to be M to the third, because you add the exponents when you multiply. So you're going to divide by M to the third on both sides. That cancels out. So therefore, K is equal to, now be careful, M over S divided by M to the third is really multiplied by 1 over M to the third. So this cancels out, right? So this becomes, I'm going to write it here, K equals 1 over S times 1 over M squared. Okay? Easy way to write that is M to the minus 2, S to the minus 1. Because when you bring something from the denominator to the numerator, you got to make it negative in terms of the exponent. Last but not least, if you have something like this is actually second order. Okay, so again, rate is M over S is equal to K. And in this case, you have M to the 1, M to the 0, and M, the 1, okay? anything to the 0 cancels out because anything to the 0 is 1. Okay, so really it's m to the s is equal to k times m squared. Divide this side by m squared, divide this side by m squared. And again, I'm going to rewrite it here. K is equal to m over s divided by m squared, or multiplied by 1 over m squared. That's the same thing. Okay, so this cancels out. So this becomes k is equal to 1 over s times 1 over m. That's the same thing as m to the minus 1, s to the minus 1. So again, the takeaway here is, depending on the order, the units for k change. If it's first order, it's s to the minus 1. If it's second order, it's m to the minus 1, s to the minus 1. If it's third order, it's m to the minus 2, s to the minus 2. What does the order really mean? Okay, and I'm just going to give you 2 examples here. Okay, what does it mean when you have, say, a blue ball, okay, to the 1? So let's call this A, this B, this C. Okay, so this becomes A, B, C. Okay, so really, what does it mean when the, let's say A is raised to the first power versus A is raised to the 0 power? What does that really communicate to us? Let's look at an example. Let's say that A reacts with B and C, but it reacts in this way, where A attacks B, then it kicks off C. C leaves because A attacked B. So this forms A, B, and then C is by itself because it's been attacked and kicked off. Okay? In this particular case, the more A you add, that means if you increase the concentration of A, okay, then the rate will increase, right? You've got more A attacking B and C, obviously the rate would increase, right? So let's look at an example, right? If you have rate is equal to K A to the 1, okay? If the concentration is 1, then the rate is equal to K, okay? If the concentration is 2, then the rate is 2K. If the concentration is 3, then the rate is 3K, right? Okay, based on this scenario here, okay? But let's say that you have a different reaction, okay, and you still have A, B, and C, okay? But in this reaction, A is super weak, so it attacks, but it can't kick off C. So C needs to leave first before anything can happen. Once C leaves, then you have A, B, and C. Now B is free, and A can attack, okay? In this case, C leaves first, okay? So that means even if you have a ton of A, if C hasn't left, A cannot attack. So even if you increase the amount of A, okay, nothing happens, right? The rate stays the same. Because C has to leave first. And if C hasn't left, it doesn't matter how much A you have, okay? So in this case, the rate order would be 0, right? If you have rate is equal to K A to the 0, okay? If you have 1 as your concentration, okay? Anything to the 0 is 1, so rate is K, okay? If you increase the concentration to 2, 2 to the 0 is still 1, so again the rate is K. And if you have a concentration of 3, again your rate is K. So notice in this case you've increased the concentration of A, but the rate in every case is still K. Okay? So hopefully you kind of have a better understanding of what the order really means. The order really depends on the mechanism of attack or the mechanism of how the reaction progresses, right? Whether or not increasing the concentration will affect the rate or how fast it goes. Okay, so if you're looking at it, you might be wondering, well, how did we come up with the order? Where did m equals 1 or m equals 0 come from, right? So if you really look at it, it depends on real experimental data, okay? And so we're just going to do a very simple example here. In experiment 1, the concentration of my reactant, N2O5, the concentration is 1 times 10 to the minus 2 moles per liter. With that concentration, the rate is 4.8 times 10 to the minus 6. Okay? Now, if you're thinking, how will changing the concentration affect the rate if you're doing this experiment? The first thing you should do is say, I'm going to do a second experiment, and I'm going to change the concentration. So that's exactly what you've done here. You've doubled the concentration. It went from 1 to 2. So how does it affect the rate? The rate is doubled. 4.8 doubles to 9.6. Okay? So because the rate is doubled when the concentration is doubled, then m has to equal 1, right? Because if m is equal to 1, then the rate law becomes rate is equal to k times N2O5 to the 1. If this was 1, okay, then the rate becomes k. Okay? If my concentration is 2, then my rate becomes 2k. Notice, my rate has doubled when I have my concentration doubled. Okay? That's exactly what this table says here. The table says if your rate is multiplied by 1/2 when you double it, your m is -1 or your exponent is -1. If your rate is the same when you double your concentration, then your m is 0. If your rate is doubled when you double the concentration, then it is 1. And when your rate quadruples when you double the concentration, then your m is 2. Basically, that's what it means, okay? The other thing you should know is how to solve for k in actual numbers with a real experiment. And so what you do is you just choose an experiment. It doesn't really matter which experiment you choose. You're going to get the same answer. So to solve for k, all you need to do, I'm going to choose experiment 1, although you can use experiment 2 and get the same answer. I'm going to say the rate is equal to k times N2O5 to the 1, okay, based on my experimental data, okay. So I'm going to pick the experiment number 1. The rate is here, right? So rate is 4.8 times 10 to the minus 6 molarity over seconds is equal to k. And my concentration of N2O5 is here. It is 1 times 10 to the minus 2 m. So to solve for k, I need to divide this side by 1.0 times 10 to the minus 2m. And I do that on this side, 1.0 times 10 to the minus 2m. 4.8 divided by 1 is 4.8. Sorry, I'm just going to write it here. K equals, okay, because this cancels out, 4.8 times 10 to the minus 6, subtract, or sorry, divided by 10 to the minus 2. You have to subtract the exponents. So 10 to the minus 4. My molarity cancels out, so I am at 1 over seconds, or seconds to the minus 1. Okay? So the actual rate law is going to be in this box here. Okay? 4.8 times 10 to the minus 4 should be up high. Okay? Seconds to the minus 1, and we know m is equal to 1, so it's N2O5 to the first power. I'm going to actually stop this video here because I think it's long enough, and continue on with this video in the next one on how to solve for orders with more complicated chemical reactions. So this is just a general introduction to rate orders. I'm going to finish how to solve for rate orders in the next video. So I'm going to call this Lecture 2, Part 2A. Okay, and the next video will be Lecture 2, Part 2B. Because this video is starting to get kind of long. So I'm going to stop it here.